So now we'll run through the calculation for the importance score, and we'll see how to go about that. And you'll see it's very mechanized, so you can use this, and you can do this for basically any web graph that you're given and follow kind of the same procedure, and it'll work out. So here's our web graph over here. Again, we've noted the links accordingly with their values. For instance, W over 2, Z over 3, and so on. The spreading of the importance scores. And we'll tabulate our equations that we just got in the last video over here, because we'll need them to solve for the importance scores, because these equations give the relationship amongst the different importance scores. And so one thing you'll notice right here is that we have 4 equations. Right, so we have 4 equations, 1 per node. We went W, then we went to X, then we went to Y, and then we went to Z. And we got 1 equation each. And we have 4 unknowns, which are the importance scores W, X, Y, and Z, as we said before. And so you'll probably remember from an algebra class or something, when you have 1 equation and 1 unknown, then you can solve for that unknown. So for instance, if you had 2x plus 3 is equal to 5, right? And you could say that 2x is equal to 2, and then that would mean that x is equal to 1, right? So, and then if you have 2 equations and 2 unknowns, that's okay also. So when you have 2 unknowns, you need 2 equations, right? Because you need two equations in order to solve for any one of those variables. Then for 3 unknowns, you need 3 equations, and for 4 unknowns, you need 4 equations, 5 unknowns, you need 5 equations, and so on. You need the number of unknowns and the number of equations to be the same if you want to have a unique solution. So to make things a little easier, we're going to look at what each of these importance scores represents. So you remember we said before that they're really probabilities. And so each of these W, X, Y, and Z is each the probability that at any given time you're going to be on one of those nodes. And we said the higher that chance is, the more important the page is, and so on. Well, things about probabilities, first of all, is that they have to always be between 0 and 1. 0 meaning it'll never happen, 100%, or 1 meaning that it's certain to happen. So if you add up W, X, Y, and Z, that has to be equal to 1, because logically speaking, you have to be on one of the nodes at any given time. So they have to add to 1 because you're 100% certain that you will be on either W or X or Y or Z at any given time. So we can make things easier by noting that these probabilities must sum to 1. And so we can say that W plus X plus Y plus Z must be equal to 1. So now you're probably wondering, well, now we have 5 equations, right? And that might be problematic because we only have 4 unknowns. Not saying that we couldn't do it, because as it turns out, you could still solve this using the 5 equations, as we will technically do, but we won't make use of each of the 5 equations when we do it. But basically, you only need 4 equations at any given time to relate these variables to one another. But this equation is much easier to use and easier to look at than, for instance, this equation right here. This equation is a little more complicated. We have a lot of divisions and things along those sorts. So this normalization equation is much easier to use. So we'll stick with that for now, and we will not use this equation. We could have also not used this one or this one or this one, but these are easier to look at because they don't relate all the variables at once. Right? This one only relates 2, this one relates 3, this one also relates 3, this one relates all 4 of them. So we use this equation with this equation, and this equation.